Hello, welcome to Don Labs. This episode we're going to be looking at diodes. As with most components, there are far too many variants to explore in one short video, so we will not be focusing on the more exotic types, just the most common ones. As this is part of my Basic Electronics series, if you would like to learn more about basic electronics, please check out my channel and watch the videos on resistors, capacitors, transistors and the principles of Ohm's Law. This series should point you in the right direction to start building basic circuits. So, what is a diode? The diode, explained in the most basic way, is a one-way valve, like a check valve. Current can only flow in one direction. So here on the bench we have 5 diodes, which we'll be covering in this video. We have the conventional SI or silicon diode, the Schottky Diode, the Zener Diode, the light emitting diode or l.e.d, and the laser diode. As you can see, the symbols for these diodes can be drawn as an outline or filled in. The symbol also helps us remember a few details about the diodes. Imagine an arrow fired into a wooden door. The triangle in the symbol is the arrowhead and the vertical line is the door. The arrowhead conducts electricity and points in the direction of conventional current, which flows from positive to negative. The tip of the arrowhead has just poked through the other side of the door, so current can flow through. Current flowing the other way hits the door and is blocked. A negative number is smaller than a positive number, so we can say the tip of the arrow is small, so this is the negative side or cathode. The other end of the arrowhead is big, this is the positive side or anode. First in our list is the silicon diode, so called because the diode is made from 2 pieces of silicon, a p-type and an n-type sandwiched together. This forms a p-n junction, much the same as in the transistor. On the silicon diodes, the stripe around the diode casing indicates the cathode, so the stripe is the vertical line in the symbol. All silicon diodes have a forward voltage of around 0.7 volts, meaning when used in your circuit you'll drop 0.7 volts across this component. So I'm going to show you 2 common uses for this type of diode. Imagine you have a battery operated device, which also has the option of a power supply to be plugged in. When you plug the supply in, you want the device to use the power supply and to block current from entering the battery in case of a non-rechargeable battery. On the breadboard we have our battery on this side here. From the battery positive into our first diode here, into a switch, and then into our motor. We have our power supply plugged in here. We have our positive from the supply coming up to the rail here, going into our diode here, into the switch in the same place as the other diode, into the motor and back to ground. When they are wired this way where current can flow, they are said to be forward biased. Notice the 2 stripes facing each other, so the current cannot go from the power supply to the battery or from the battery to the power supply. It can only flow through the switch when the switch closes. So I'm going to connect an ammeter between the first diode and the battery. So I've connected an ammeter between the first diode and the battery, and I'm going to close the switch with just the battery connected. So when I press the switch, we get 53 milliamps. Now I'll turn the power supply on, and the higher voltage power supply should mean the battery no longer supplies a voltage or allows current to flow, and no current will flow from the supply to the battery, which we can confirm on the ammeter when I press the switch. It stays on 0 when the motor's running. This type of diode is also used to change or rectify alternating current to direct current. This is called a bridge rectifier. On the breadboard this time we have the 555 timer circuit generating an alternating current. Connected are 2 LEDs, and we can see the LEDs are alternating. Now if I change the ground wire for the LEDs, take that out and replace it with a diode, you'll see only one is flashing. We have taken away the negative part of the alternating signal. If I turn the diode around, face the other way, put it back in, You see the other LED is now flashing. We've taken away the positive half. This is called half-wave rectification. If we use 4 diodes in a full bridge configuration, which you may have seen drawn like this, or this, then we flip the negative half of the signal and place it over the gaps in the positive half. With a square wave, like the circuit I'm using, we will get a nice constant output, but if you were to rectify a sine wave, you would need to use a smoothing capacitor to smooth out the peaks of the wave. If the current is greater than an amp, you may find that the silicon diodes are referred to as rectifiers, regardless of their function in the circuit. Next on our list we have the Schottky Diode. They can be in a similar casing to the silicone diode, but also come in a different TO packages like the TO220 here on the breadboard. The Schottky is constructed the same way as the silicon diode, except one side of the silicon has a metal contact. This increased conductivity makes for a far lower forward voltage than the silicon diode, so you'll only drop in between 0.15 and 0.46 volts as opposed to the 0.7 in a silicon diode. This also means you can achieve far greater switching speeds and recovery. Recovery of the silicon diodes can range from several microseconds to a few nanoseconds, whereas the Schottky diodes are about 100 picoseconds, which is practically instant. The drawback of the increased conductivity means the reverse leakage current is higher. If we go back to our arrowhead analogy, remember we said the arrowhead conducts electricity and the door blocks it. Because the tip of the arrowhead has poked through, there is a tiny area where a small current can flow back through. Every diode can leak a tiny amount of current through the wrong way, but it's so small it's almost insignificant. You do have to be wary with the Schottky, however, as it's enough to affect some circuits. Due to this faster switching, Schottky diodes are also used extensively in switch mode power supplies, where frequencies can go as high as 2 MHz. The third diode we'll look at is the Zener Diode. Most of the Zener diodes will be in a package similar to the silicon rectifier but with a clear casing. Not always the case, so check part numbers if you're not sure. All diodes have a breakdown voltage. Back to the arrow again. When conventional current is hitting the door, there is a limit to how much pressure or voltage the door can take before it bursts open. Any diode will conduct in the wrong direction once this breakdown voltage is reached. This is called reverse bias. This will invariably lead to the diode becoming damaged and of course probably your circuit too. Zener diodes are actually designed to be able to conduct in reverse bias at a specific voltage. This is a 5.5 volt Zener, so will conduct in reverse bias once 5.5 volts is reached. They're designed to break down with more control, so they will limit the reverse bias voltage to the Zener voltage. In the datasheet for the diode there will be a reverse bias current also. This means that below the minimum the reverse bias voltage may be less than the Zener voltage and unregulated. This makes them very useful for using as voltage reference in a circuit or providing a stable voltage output when the input is subject to fluctuations. There are two different ways in which Zener diodes operate, but to keep it simple, a Zener below 5.6 volts is normally firmly stable, and over 5.6 volts will have more and more significant heating as the Zener voltage increases. So here on the breadboard we have our 5.5 volt Zener diode. We can see our trusty LED connected up with the current limiting resistor. The LED is lit and the voltage across the diode is 5.5 volts. Now as I adjust the voltage on the power supply, it's a 12 volt supply, so I can turn this all the way up. That's its limit there. Still 5.5 volts across the Zener diode. Start turning it down. Still 5.5 volts. If I move the voltmeter to the power supply, we can see there it says 8.8 volts, and I'll just show you that it does actually go all the way up. Coming to the end of our list, we have the light emitting diode, which we already have used a couple of times in this tutorial. Each colour has a different forward voltage. When using them, you can either look at the datasheet or just screenshot this. As explained earlier, the diode is a PN silicon junction, and as such the resistance is variable. It will go down as more forward bias voltage is applied. This is not a linear relationship as in Ohm's Law, but a sharp curve. As you get past the knee, the current rises very quickly in comparison to the voltage, and the LED will melt or explode. To this end, you have to use a current limiting resistor. Most small LEDs from 3 to 5 to 8 mil are usually rated for a maximum of 20 milliamps, but just check the data sheet just to make sure. This is a maximum, remember, so you don't have to abuse them to get full illumination. Most cases with modern LEDs, 10 to 14 milliamps is plenty. To work out the resistor needed to achieve your desired current, we use Ohm's Law, as unlike the diode, the resistor in the circuit has a known fixed value. As we want a maximum current of 15 milliamps, this is slightly below the reverse current of the Zener, so Zener voltage will be closer to 4.9 volts in this case. Deduct your LED forward voltage of 3 volts to give us the 1.9 volts, and this is across the only other component, the resistor. So R equals V over I, so 1.9 divided by 0.015 gives us 127 ohms. I'm actually using a 220 ohm resistor this time, so if we plug that value back into the formula, I equals V over R, so 1.9 divided by 220 gives us 0.0086 amps or 8.6 milliamps. And as you can see, the LED is still fairly bright. Ammeter in between the resistor and the diode. And we're getting 8 milliamps. Last on the list we have the laser diode, or light amplification by stimulated emissions of radiation. Like the LED, a laser diode emits light, but it's monochromatic and coherent, so it's one specific colour wavelength and all of the photons of light are parallel and moving in the same direction. Just a warning, if you're planning on playing around with a laser, they are very dangerous and can cause blindness even from reflections off dull surfaces. Also, they can cause burns and fires, so please be careful and always wear eye protection. You can get laser glasses for the specific laser wavelength you are using. Laser diodes have rather sensitive current requirements similar to the LEDs, so have to be used in conjunction with a driver circuit. This will provide a constant current to the laser diode whilst also limiting the maximum voltage that can be reached. This is how these particular lasers are being powered right now. It's a very, very small circuit and it's right inside there. And this one here comes out of a laser pen, so the circuit board is a little bit bigger, but it's actually still attached to the laser diode, which is this section here. And obviously if you didn't have this, you would have to build a current limiting driver circuit, which looks similar to this power supply here, but instead of supplying a constant voltage, would supply a constant current. More powerful lasers can get very hot, so we'll also need additional cooling on the diode itself and also the driver circuit. And one of these heat sinks here were generally used on the driver circuit, as it is used in this voltage regulator here. And also you'd have a heat sink casing which encased the whole diode itself. The diode is actually a small part inside this casing here. So that's the end of the list. It's only a basic demonstration of the diode, and the next series will delve even further into several of the basic features we've talked about in this whole series. Don't forget to like and subscribe. Thanks for watching, and don't blow up.